Proof by induction is the second type of proof I am going to explore in this series, following on from direct proof. You will see some aspects of direct proof within this, and I am still going to be talking about the logical steps covered in the first episode. You can see from the definition that proof by induction has two stages to it. I want you to focus on this structure whenever you are completing a proof by induction question. In this video, I will explain why this structure works, and I will also talk about the structure within the second stage that we will be able to apply to various different types of proof by induction question. So the first question to address is, why does proving true for the base case, in this question when n equals 1, then proving true for n equals k plus 1 when assuming true for n equals k, work? Why is it a valid proof that means the statement is true for all integer values of n? The key is the base case, because then k can start off as being 1, so the assumption is true, and then we are proving true for n equals 2. It can now be true for n equals 2, as we've just proved it, so we can set k as equal to 2, and thus proving true for n equals k plus 1 will mean proving true for n equals 3. Then we know n equals 3 is true, so we can repeat the process with k equals to 3 to then prove that n equals 4 is true. This spiral argument can keep on going on and on infinitely many times. This is why some people often refer to proof by induction as knocking down dominoes. Once you know the first one falls down, then it will have an effect on the second, which will have an effect on the third, and so on. Some people also use a ladder metaphor, where instead of knocking down dominoes, you are climbing a ladder one rung at a time. And because you can go up the first one to get on the ladder, the process is the same to keep on going up it. It is worth pausing to reflect on this before moving forward and looking at how to set out this argument in relation to a question. Firstly, I'm going to apply this to the sum of squared numbers. The base case, the first rung, is when n equals 1. I can evaluate the left-hand side and evaluate the right-hand side, quite simply. Therefore, it is true for n equals 1, because the left-hand side is equal to the right-hand side. I advise you to keep the same structure I am using. Then assuming true for n equals k is just a statement. Now comes the part where we need to explore the proof in order to form a general approach. When n equals k plus 1, I want to start with the left-hand side of the statement and work my way to the right-hand side. This is like a direct proof, so I want to know what I am heading towards, what my goal is. The goal is the right-hand side of the statement, but with k plus 1 instead of k. Knowing this will help me form my logical steps. Writing out the left-hand side for n equals k plus 1, I can see that I have the left-hand side of the assumption, but with an extra term on the end. As I have assumed n equals k to be true, I can replace the first k terms with the right-hand side of the assumption. And I still need to add on that final term. Now I have reduced the problem down to the sum of two expressions. My goal is one fraction, so it makes logical sense to combine the two expressions into one fraction. It now makes logical sense to factorize out k plus 1, as my goal has a factor of k plus 1 at the beginning. I can then expand the second bracket and factorize to get the desired result. You should be able to see similarities in my explanation of this final step to those I gave in the first episode. To finish off the proof, I need to make this final statement. The next question will add an extra step to the proof involved when n equals k plus 1. In order to make this step clearer, Let me just go through sigma notation. There are three parts to sigma notation. The starting value at the bottom of the sigma symbol, the last term, which is at the top of the sigma symbol, and then the general term, which is to the right of the sigma. We start by substituting in the starting value into the general term. So, for example, if we are making the sum from 1 to 6, this will start with r equals 1. This will be followed by the next integer, r equals 2, and keep going until r equals 6. Therefore, there are 6 terms. We can therefore express this summation using sigma notation to represent the first 5 terms and add on the last term. We can do a similar thing when summing up to n. The key point is that we have the correct number of terms in the expression. You should keep this manipulation in mind, as we are going to see how it is helpful for the question above. Now back to the question. I'm keeping the same notation as with the previous question, looking at the left-hand side and then looking at the right-hand side, and making the final statement that the left-hand side is equal to the right-hand side, therefore is true for n equals 1. Then assuming true for n equals k is again a statement. Now we get to the interesting part, when n equals k plus 1. You can see here that I've written down my goal, and I've just simplified it so that it'll be easier for me to see it. In the previous question, I could substitute the right-hand side of the assumption as I had the left-hand side of the assumption from the start. I don't have that now. I have the sum of k plus 1 terms. But I want to have the sum of k terms so that I can make that same substitution. Using what I was referring to before, I can split this summation up into the first k terms plus the k plus 1th term. Now I can make my substitution for the first k terms and substitute k plus 1 into the general term of the sequence to get the k plus 1th term. After the substitution, I need to think logically. My target is an expression with plus 2 at the end. I already have this, so I will leave it alone. The other two terms I need to combine into one, and I can do that by factorising. They both have a common factor of 2 to the power of k plus 1. After simplifying, I can see I am still not at my target, as I need 2 to the power of k plus 2, not k plus 1. Well, I am multiplying 2 to the power of k plus 1 by 2 and then by k, so I can combine this extra 2 into the power to give me my desired result. And the last step is to make the statement. We need to generalize the approach when n equals k plus 1, as this is the difficult part of the proof and the part that requires a step-by-step process. When n equals 1, and writing down the statement assuming true for n equals k, are relatively straightforward. To begin with, I started off with the left-hand side of the assumption, but for when n equals k plus 1 instead of k. I then manipulated this by breaking it up into the sum of the first k terms plus the k plus 1th term in order to get in the left-hand side of the assumption. The next point is to substitute in the right-hand side of the assumption before then manipulating to reach the goal, much like I did in the direct proofs in the first episode. In the next type of question in this episode, and in the next episode, I'm going to stick to this method, and I'm going to approach n equals k plus 1 in the same way each time to show you that you don't need to learn a different process for each type of proof by induction, and you will be able to face whatever imaginative question the examiner throws at you. The next question looks at proving an expression is divisible by 4. We can alternatively look at it as proving that the expression is a multiple of 4. Firstly, there is no left-hand side or right-hand side, but we can substitute 1 into our expression to prove that it is true for n equals 1. The assumption is that when n equals k, 5 to the power of k minus 1 is a multiple of 4, and therefore equal to 4a for some integer a. Now my goal for when n is equal to k plus 1 is to get an expression that can be of the form 4 times some integer. Now I want to show that the structure still works for this divisibility question when n is equal to k plus 1. Firstly, the left-hand side of the assumption when n equals k plus 1 will be 5 to the power of k plus 1 minus 1. In order to be able to substitute in the assumption, I need to work in 5 to the power of k minus 1, so it makes logical sense to rewrite 5 to the power of k plus 1 as 5 times 5 to the power of k. I still don't quite have 5 to the power of k minus 1 though, because of the multiply by 5. I can, however, factorize this 5 out, and then correct myself at the end to make sure the two expressions are equal. To do this, I need to add 4. Just pause the video for a moment and expand this line to check that it does indeed equal to the previous line. I can now substitute in and then factor out the 4 to get an expression that is 4 times some integer. The process for when n is equal to k plus 1 was the same as for the series questions, and you need to replicate this in each proof by induction question you encounter. This is always my approach and always what I am looking to do. I will go through another example of divisibility to show you that just because there are two terms with a variable power, the process does not change. Again, for n equals 1, the process is the same, and my assumption and my goal are also the same. I want to finish with an expression of the form 4 times an integer. When n equals k plus 1, I will again substitute this into the left-hand side of the assumption before taking out the plus 1 in the power to make it look more like the left-hand side of the assumption. I can then factorize again and correct myself in order to substitute in the right-hand side of the assumption. Again, you can expand the bracket here to make sure that it is equal to the previous line. Now I can factor out 4 to get my goal. My point of this episode is to get you used to the structure for the final part of the proof by induction when n equal to k plus 1. In the next episode, I want you to see again that this structure works, so you do not need to learn a different approach for each type of question, but you can use a general approach that will work no matter what the exam throws at you. We have looked at series and divisibility proofs in this episode. In the next episode, I will present examples from differentiation and trigonometry, keeping this same structure.